Welcome to my lecture on waves at material boundaries. In our last lecture, we learned the behavior of fields, which means electrical or magnetic fields at material boundaries. And now we are going to apply this to the behavior of waves at material boundaries. That means how waves, electromagnetic waves, are reflected or transmitted at material boundaries. We will derive our equations for plane waves, but we already know that we can express any wave by a superposition of plane waves. So that means the solution for plane waves is a general one. This figure shows the definition of our coordinate system with x, y, and z axis. We define it in such a way that the material boundary is equivalent to the yz plane, and the incident wave vector as well as the reflected wave vector and the transmitted one is located in the xz plane. That means that the wave vectors look like that. So, for example, the incident wave vector goes to in minus x direction. So we have minus sign here, and it's given by cosine, of course. And in y direction it is 0, because we choose our coordinate system in such a way, and it goes into positive z direction. And in case of the reflected wave vector, this one goes to positive x direction and positive z direction. So you can find all wave vectors here. The wave vectors are quite important to calculate the spatial phase, which is given as a scalar product of the respective wave vector and the x, y, z spatial vector. At first, we will have a look on the TE wave. That means a plane wave, which is S-polarized, and that means that the electric field is parallel to the material surface, which in our case means it is polarized in y direction. Later we will also discuss the TM wave, where the magnetic field is parallel to the surface. So, and here in this figure you can see all the definition of all these vectors, as well as the respective angles, the incident angle, the reflected angle, and the angle of the transmitted wave. On the right hand side you find all the fields. So the incident electric field is given by its polarization vector y and an amplitude and a phase factor. In the phase you have this scalar product, and this is carried out already. So the scalar product of this xyz vector with ki is given here. And k, by the way, is 2 pi over lambda, the wavelength of course. Yeah, there is nothing special otherwise. Maybe N1 is of course the refractive index of material 1, and in the electric field of the reflected wave is there's not much difference. Of course, the amplitude is different. We have to calculate the amplitude later on, and the angle is different from the incident angle. and of course here is a minus because here we have plus, and therefore the sign is switched at this point. So, and the transmitted electric field is equivalent to the incident field, with the exception that the refractive index is now N2 and not N1. And of course the index is T and not I. It's quite important that we can define ourselves the amplitude of the incident field, of course, and the angle of the incident field. But we have to calculate the amplitude of the reflected field and the angle of the propagation angle of the reflected field, as well as the amplitude of the transmitted field and or wave, and the propagation angle of the transmitted wave. So down here you see the magnetic fields, the respective magnetic fields. Of course, the polarization is now different. It's not just in y direction as the electric field, but perpendicular to this. So in the x and z plane. And multiplied by the respective sine and cosines of the incident, reflective and transmittive angle, of course. You can see that, for example, the incident magnetic field goes in negative x and negative z direction, so minus and minus, and the reflected magnetic field goes to negative x and positive z direction, and that's the reason for these signs. Then the next factor is the amplitude of the magnetic field, but we express it by the electric field, and we already learned in, I think, the last lecture that we can express the amplitude of the magnetic field by the electric field, but there is an additional factor, which is the impedance. We used the impedance of vacuum here and added the refractive index, the respective refractive index. So in total, this factor of diffraction and EI is the amplitude of the magnetic field. The phase factor is exactly the same as here. Yeah, and now we do the same for the reflected magnetic field and for the transmitted magnetic field. So again, phase factor is the same, and the only difference here is for the transmitted field, we of course have to use the refractive index of the second medium. In the last lecture, we derived the boundary conditions of the electric and magnetic fields. The conditions say that the component of the electric field parallel to the surface, the boundary surface, is the same on both sides of the boundary, in material 1 as well as in material 2. And the same holds for the magnetic field. In our case, the boundary is defined by x equals 0, because the boundary is equivalent to the YZ plane. The electric field of the TE wave is polarized in Y direction, so the electric field in total is parallel to the surface. Therefore, we can apply the first condition directly to the electric field. The only thing which we must be aware of is that in material 1 we have two fields, the incident field and the reflected field. So we have to build a superposition of these two fields. Yeah, and the phase factor is reduced somehow because x is 0, and therefore the first term in the phase of the phase vanishes. Yeah, and the left-hand side of this equation is the field in material 1, and the right-hand side is the field in material 2, which is the transmitted field. In case of the magnetic field, we must be a little bit more careful because the magnetic field has a component in x direction which is perpendicular to the surface, and we have to skip that because the boundary condition is only for the part which is for the component which is parallel to the surface, and this is the z component. And therefore we have this cosine factors in all three terms. Again, we have to add the incident and the reflected field, and which in total give the magnetic field in medium 1, and in medium 2 we have just the transmitted field. The minus at this point just comes from the respective sign of the magnetic reflected magnetic field. So now we end with two equations, and these equations are complex equations. However, the equations must be valid for any incident plane wave, so for any amplitude and any incident angle. And that can only be the case if these equations are both fulfilled for the phase and for the amplitude independently. And therefore we split the equations to phase condition and later on the amplitude condition. So first of all, the phase condition says these equations can only be fulfilled if all phases are the same. And actually the phases of the second equation are the same as in the first equation. So we have just this phase condition. This phase as well as this one and this one must be the same. There are a couple of common factors which are skipped here. So I is a common factor, k is a common factor, and z is also a factor which is in all phases. And therefore the remaining factors are the ones given here. We have two equations actually. And the first equation can so the equation of the first two terms can be simplified because there is a common factor n1 which can be skipped, and then we end with the law of refraction, which says theta I, the incident angle, is the same as the reflected angle, or the other way around usually. So this is the well-known law of reflection. And the second condition is given by this equation, and this is actually the well-known Snell's law of refraction, which is shown here. So we found that the phase condition fixed the direction of propagation for the reflected and the transmitted wave. However, we still don't know the amplitudes of these two waves, and that is what the amplitude condition delivers as. Now we know already that all these phase factors are the same, and therefore we can skip them from these equations. And then we end with these two equations here, but we already applied the law of refraction and substituted theta r by theta I. Please note that we did not the same for theta t. We could express theta t as a function of theta I also by using Snell's law, but this leads to some problems or important points, and therefore we keep theta t for the moment. Okay, so in the first step, we use the first equation and insert it in the second one, in ET. And then we get an equation with 4 terms, and in the next step we sort the terms with EI factor on the left-hand side and the terms with the common factor ER on the right-hand side, and that allows us to calculate the amplitude reflection factor, which is the relative amplitude of the reflected wave, relative of course to the incident amplitude, and the expression is given here. You could also do all these calculations with the amplitudes of the magnetic field instead of the electric field, and in that case you would get this almost the same result, the same expression, but just the opposite sign. So RH is minus RE. And this is actually Fresnel's law of reflection. However, there is also a Fresnel law for transmission, which defines the amplitude of the transmitted wave. And we can derive that when we solve the first equation by ER and insert this value in the second equation. Again, we get an equation with 4 terms given here, and we sort them in such a way that we have all EI terms on the left side and all ET terms on the right side, and that allows us to calculate the amplitude transmission, which is the relative transmitted amplitude, and the expression is given here. If we would carry out the same calculation with the magnetic amplitudes, field amplitudes, then we would have N2 instead of N1 here. So there is the amplitude transmission of the magnetic and the electric fields are different by this factor. Again, let me remind you that we still have this theta t in this term, and now the next step will be a closer look on this factor. As already mentioned, the direction of propagation for the transmitted wave is not a free parameter anymore. It is fixed by Snell's law, actually. However, Snell's law gives the sign of theta t only, but Fresnel's law requires the cosine. As you know, of course, you can convert the sine to cosine by sine square plus cosine square equal 1. And the result is given here. However, you should keep in mind that the sine is squared here, which means that you lose information on the sine of the right-hand side here. So finally, when you take the square root of this argument, you don't know whether you have to take the plus or the minus sign. This is not clear from the mathematical point of view, and you have to use physical considerations to decide which of these two signs is realistic physically and which leads to an unphysical situation. But before we decide that, we should also note that the argument of the square root may become negative. This and the critical angle at which that happens is given by this expression. When the right term becomes 1, the argument is 0, and that is exactly the critical angle. And of course you can solve that for sine theta I, or critical angle is named theta c in this case. You also see here, since the sine function is limited by a magnitude of 1, this can happen only in cases where n1 is larger than n2. And in fact, this critical angle means total reflection, or total internal reflection as it is named. And you can easily prove that if you insert this in Snell's law, because then you find the right-hand side is 1, which means theta t is 90 degrees. And that's actually no transmission, because then the transmitted wave is running parallel to the material surface. And there is no transmission actually anymore. Which means that you have 100% reflection and no transmission. As soon as the argument becomes negative, then you can take out the square root of -1, which means I, and have two different cases here in this expression. The first case is the standard one with usual reflection and transmission. In this case, we took the plus sign, and we can prove that when we have a look at the wave of the transmitted wave. And what we need to take into consideration is the first term of the phase, because here we have the cosine theta t, and we see that the transmitted wave propagates in the same x direction as the incident wave. So the incident wave goes to negative x direction, and therefore the transmitted wave also has to propagate in negative x direction. And due to the sign convention we used, this means positive sign in this exponential. And we achieved that when we use the positive sign here also. So that fixes the sign in the conventional case. However, if we take the case of total internal reflection, then we can take out the square root of -1 here. That is the I, and of course then we have to switch the two terms inside. That makes sure that even in that case we have a real argument here, and the cosine theta t is purely imaginary. That means when we insert it here, we have I times I is -1, and we choose minus here also, so in total it is +1. Which means we don't have a periodic function anymore, because there is no I left. It is a real argument of the exponential function, and therefore the exponential function is decreasing with increasing negative x values. So when x goes to minus infinity, the exponential function goes to 0. And that is exactly the behavior which we need. And if we would have taken the plus sign here, we would get an increasing electrical field to infinity. So that would not make any sense. So we know now that we have to take the plus sign in the convention for the conventional reflection and transmittance, and we have to take the minus sign in case of total internal reflection. Let us finally have a closer look on the amplitude reflection in case of total internal reflection. We already know that the intensity reflection must be 100%, of course, but the amplitude reflection factor is a little bit different. So we use the expression we just derived, but insert our expression for the cosine theta t at this point. We see that we get a fraction with numerator and denominator of the same magnitude, but the denominator is the complex conjugate of the numerator, which means actually that the magnitude of the amplitude reflection is actually 1. That's not surprising because the square of the amplitude reflection factor is also 1. However, it is a complex number with magnitude 1. However, so in order to get the value of this complex number, we have to multiply numerator and denominator with the value of the numerator. So therefore, we have this squared, and in the bottom we have a complex number multiplied by the complex conjugate of the same number, and therefore we end with this expression, which is a real number, of course. And now, this is just a small modification here, and then we can state that since we know that this is of magnitude 1, we can also write it in such a way. We can define an angle psi TE for TE wave. We will see that in case of the TM wave, this angle is different. And we introduce a factor 2, which is not necessary, but we can do that, of course, because that fits to this square here and allows us to define the angle psi TE by just by a tangents of this imaginary and the real part of this number here in this expression, in the way which is shown here. So this is the expression of the tangents of psi TE, and this in fact that means that we have a phase shift in the reflected wave, which we don't have in case of normal reflection, because when we have normal reflection, the reflection factor is just a real number, so there is no phase shift. But as soon as we have total internal reflection, RA becomes a complex number, and we have this to take into account this phase shift. That becomes fairly important in case of optical waveguides, as we will see in our next lecture. So now we know the amplitude as well as the angle of propagation for the reflected and the transmitted wave in case of the TE wave. And now we will do the same derivation for the TM wave, which means p-polarized waves or magnetic field parallel to the surface of the material boundary. If you have a plane wave with arbitrary polarization, you always can split it into a TE wave part and a TE wave component and a TM wave component. So when we have the expressions for the TE wave and the TM wave, we are finished and have the general solution. Okay, now in this figure you can see all the definitions of the electric and magnetic field vectors for the incident wave and for the reflected wave and for the transmitted wave, and of course again the angles. The wave vectors are exactly the same as in case of the TE wave, but the fields look a little bit different. In this case, the magnetic field is polarized in y direction. The amplitude of the magnetic field is exactly the same as for the TE field, of course, and the phase is also the same. The only difference is the polarization, which is y in case of the magnetic fields, and in the xz plane in case of the electric fields. Yeah, for example, here for the incident field, you see here positive x and positive z direction, well, plus and plus. And in case of the reflected field, positive x direction, negative z direction, plus and minus. And the phase factors are the same as for the TE wave. Now we again apply the boundary conditions for the electrical and the magnetic field at the position x equals 0, of course. And in that case, again, the sum of the incident and the reflected field on the one side, so in medium 1, is the same as the transmitted field in medium 2. However, this is only the case for the parallel part of the field. And now we therefore have to take the z component of the electric field and skip the x component, which is perpendicular to the surface. And this gives the first equation. And the second equation is it comes from the magnetic field, and in that case we have a y polarization which is always parallel to the surface. So this is the easy one. Again, we have two complex equations, and they must be valid for arbitrary amplitudes and angles EI and theta I, and therefore they must be fulfilled for the phase as well as for the amplitude. The phase condition, however, is exactly the same as in case of the TE wave, because the phase factors are the same. And therefore we again get the law of reflection and Snell's law of refraction. So, however, the amplitude conditions are a bit different, because now we have these cosine factors in the first equation and not in the second one. That's the most important difference. And again, we used the law of reflection here and substituted theta r by theta I. But also, in the same way as for the TE wave, we kept theta t, although we know that this is not a free parameter anymore, but it is fixed by Snell's law. It is a function of theta I. In this case, we solve the second equation for ET and insert that in the first equation, and then we get an equation with 4 terms, and we sort them with EI on the left side and the R terms on the right hand side, and then we finally end with the amplitude reflection factor of the electric field, which is given by this expression, and again for the magnetic field amplitudes we get the opposite sign. This is Fresnel's law for TM waves. And by the way, I realize just now that I did not mention what TE and TM actually means. TE is transversal electric, that means electric field parallel to the surface, and TM means transversal magnetic, which means magnetic field parallel to the surface. So, in addition to the Fresnel law for reflection, we also have a Fresnel law for transmission, and we can derive that when we solve the second equation for ER and insert that in the first equation. Again, we end with an equation with 4 terms, and we sort them for EI and ET, and then we end with expression for the amplitude transmission factor, which is very similar to the case of the TE wave. Both expressions for reflection and transmission are almost the same. The only difference is that N2 and N1 is exchanged, and here it also exchanged. However, N1 in the numerator of this fraction is the same as for the TE wave, but it is exchanged again when you use the amplitudes of the magnetic field. So this again is the same as for the TE wave. So we finally are completed. So we know now the direction of the reflected and the transmitted wave, and we know the amplitude. However, in the same way as for the TE wave, we have to take some considerations for the case of total internal reflection. But for this derivation, for the TE wave, we only used Snell's law, and Snell's law is the same for TE and TM wave. So all we did here is exactly the same for TM wave. We can immediately use this expression in our case for the TM wave. So we switch to the next slide and calculate the phase shift at total internal reflection. And this is actually somewhat different for the TM wave than for the TE wave. The calculation, however, is done in exactly the same way. We insert cosine theta t by this expression. And of course, we see that now we have in the numerator and denominator of this fraction, we have the same complex number, but in complex conjugate form, which means again that the magnitude of this factor is 1, and that allows us to say that this amplitude factor must that we can express this amplitude factor in such a way with an imaginary power of E. And again, we use this factor 2 because we have a square here, and we define this angle CTM now, and we get this expression. It's just the quotient of this one and this one, this term. When we compare it to the case of TE, we see that there is just an additional factor of n1 over n2 squared. Everything else is exactly the same. And this is the phase shift which we get in case of total internal reflection, and the phase shift for TM polarization is different than for TE polarization. Just for the sake of completeness, I would also like to mention the special case of the Brewster angle, which is the angle of incidence where the amplitude reflection becomes zero. This can only happen in case of the TM mode. The TE mode is always larger than zero. The reflection factor of the TE mode is always larger than zero. However, if we take the expression of the amplitude reflection in case of TM mode, we can easily see that this becomes zero only if n2 times cosine theta I is equal to n1 times cosine theta t. Now we substitute cosine theta t by the respective square root expression, which we already derived, and then we end with this expression, and theta I is substituted by theta b, the Brewster angle. Okay, now we square this equation on both sides and divide by n1 square, of course. And then we end with this equation, and there the cosine square is substituted by 1 minus sine square. And here we have the argument of the square root, of course. Now we collect the terms with factor sine square from both sides, here on the left side, and all others on the right-hand side. So here we have plus n1 over n2 squared minus, this is this minus n2 over n1 squared times sine squared theta b. And on the right-hand side, 1. And from this one, we have this n2 over n1 squared. Now in the next step, we go to common denominator here, and which gives us n1 to the power of 4 minus n2 to the power of 4 here, and on the right hand side n1 to the power of 2 minus n2 to the power of 2. In the next step, we use the fact that n1 to the power of 4 minus n2 to the power of 4 is equal to the product of n1 squared plus n2 squared times n1 squared minus n2 squared. And this is important because then we have this factor, this minus factor on both sides. These cancel out, and n1 squared is the same here on both sides, so these also cancel out. And when we bring this fraction to the other side, we finally have n2 squared, this is this one, and we have n1 squared plus n2 squared, which is the residual from this power of 4 term. And finally, we substitute the sine square by a tangent square. You can find this expression in a mathematics textbook, of course. That is a standard expression. And when we compare both sides, we easily see that that means the tangents theta b is equal to n2 over n1. This is the definition or the expression for the Brewster angle. So now we are finished, and let us collect the results of the amplitude factors given by Fresnel's law, because that is quite instructive. Now we have the intensity reflection in this on this axis. That means the square root of the amplitude reflection factors. In case of an incident angle of 0 degree, TE and TM waves are equivalent, because in that case the electric as well as the magnetic field is parallel to the boundary, and both expressions lead to the same factor, which is given here, n1 minus n2 over n1 plus n2, and this squared. This is the well-known expression for Fresnel reflection in case of perpendicular incidence. In case of TE waves, you get this curve for increasing incidence angle. In cases where you have where n1 is larger than n2, you have a critical angle of total internal reflection, and from that angle on you always have reflection 1. If n1 is smaller than n2, then you would reach 100% reflection at an incidence angle of 90 degree. So then you would just have no total internal reflection. And in case of the TM wave, the reflection is reduced at first and goes down to 0 at the Brewster angle, and then is increasing up to 100%, either at the critical angle of total internal reflection or at 90 degree if there is no total internal reflection. Okay, so that's all for today. We used the boundary conditions for the electric and magnetic field at material boundaries to calculate the reflected and transmitted plane wave from an incident plane wave. And we will use that in the next step to describe waveguides. And in waveguides, we actually need the case of total internal reflection. And that's actually the reason why we also calculated the phase shifts for both kinds of waves, the TE wave and the TM wave. And we will use that in the next lecture. Thank you for watching.